All right, let's go ahead and get started. Before we do, just a reminder, I dropped an announcement on Canvas last night. Take a look at it if you haven't already, but basically gave some details about the final. Exam 3 is in the grade book now. If anybody wants to have a quick chat about kind of where they stand, obviously have a much better idea of that now than I did before the test, but yeah, if anybody has any questions about anything, please let me know. We have 2 sections left to cover. They're both going to be on the final. And I think all the assignments. All right, any questions before we get started today? All right, so we're going to get a little deeper into how to evaluate definite integrals. So to do that, let's just start with some generic function f on some interval a to b. And really what I'm looking at is this thing. I want to find the difference between basically the y values at the ends of this function. So if I can draw a graph up here to help us, some interval AB, some function defined on that interval. Basically, I'm trying to integrate over this region here. So let's build that up slowly. So one thing I'll say, just to represent A and B in a different way, is I'm going to call A x sub 0 and B x sub n. Because what you're just looking for here, here's what I want to do. I want to take that area, and kind of like we've already been doing, I want to break it up into smaller areas. So to do that, basically I want to, did I use the word partition with you all in regards to integrals? Basically what I'm going to do here is I'm going to take this x interval and partition it into many smaller little subdivisions. So in doing that, let's look at this. First thing I'm going to do is just going to substitute x sub 0 and x sub n for my a and b. But instead of just having one rectangle, because that's a really terrible estimate, I want to start building up many and many of these. So I'm going to do it this way. I'll do f of x of n minus f of x sub n minus 1 plus x of sub n minus 1 minus f of x sub n minus 2, all the way down to f of x sub 1 minus f sub x of 0. And I'll pause there. For example, at these 2 terms. So in this top line here, I didn't have this f of x sub n minus 1 term, but now I do. But look at what I'm doing with it. I'm bringing it in as a positive term, but I'm also bringing it in as bringing in its opposite, bringing in its negative. So what's going to happen to basically all of the middle terms in this calculation here? They're all gone, right? So I still really do, in effect, have f of x sub n minus f of x sub 0. But the reason I brought these things in is now I can represent this way. This sum from 1 to n of f of x sub I minus f of x sub I minus 1. So as I'm going through this, I'm going to be building up, well, basically I'm just doing a lot of algebraic manipulations, not just. It's going to get pretty complicated, but as I do, please ask me questions. if you're not understanding how I'm making these little leaps. The right-hand term that's not here, this is x sub I minus 1. So basically think about I think it's probably helpful to think about, all right, when I equals 1, what am I doing here? What's this term going to look like? It's going to be f of x sub 1 minus f of x sub 0, which is the very last calculation that I wrote down on the line above it. On the other hand, when it counts all the way up to n, I'm going to have f of x sub n minus f of x sub n minus 1, which is the very first calculation. So basically, I've just compacted all of these things that I'm adding together into this summation notation. Does it matter how many times I do this? Does it matter how large I make n? No, because of that, I can say that I can basically limit this thing. It really does not matter how many times I want. Like, it doesn't matter how fine I make the partition of that x interval. This is always going to be true of this equality. Are we okay so far? All right, now here's something I want to do. Let's take a departure from, let's just look at this individual f of x sub I minus f of x sub I minus 1. So make some space for it. So if I take f of x sub I minus f of x sub I minus 1, doesn't matter what I is. And I want to do this. I want to divide this by x of I minus x of I minus 1. This calculation here, what am I doing? So from here, I can say this for sure. I can say that this thing right here, this slope, is going to be equal to the derivative of my function somewhere in this interval. Why do I know that overall slope and so why do I know that average rate of change in that interval? Something we've done somewhat recently. That's the mean value. So because my function is continuous, and I know somewhere my slope is going to be equal to like the average rate of changes. So somewhere on every single one of these little intervals, no matter how small I make them, I can pick a sample point whose derivative is the same as the slope. One more thing I want to do here is this. I'm going to multiply through by that denominator and get this f of x sub I minus f of x sub I minus 1 is equal to f prime of xi star times x sub I minus x sub I minus 1. So before I go back to our main proof here, are we okay with this manipulation I did? Because now I want to make that substitution. All right, I'm going to go ahead and substitute here. Still have the limit as n approaches infinity, but now of this new thing. F prime of x of I star times x of I minus x of I minus 1. Have we seen this thing before? Oh, I've been leaving off something really important. For some reason, somewhere I dropped this sum. I really am adding all these things together. So now what I have is a Riemann sum with some delta x. So I have I'm adding together all these products of some function evaluated at some point multiplied by all these delta x's. And I'm limiting that. I want n to get arbitrarily large. So when I limit a Riemann sum this way, that's basically the definition of what other thing that we've been dealing with. This right here is an integral. This definite integral from a to b of this function. I'll stop here to ask a couple of questions. First of all, anybody need me to unpack anything as far as like any of the manipulations? Top line and bottom line. And how is function now related to this inside the interval? Cameron?
So going from the second one to the third one, is that part that's in like the brackets? Is that what? The third line is equal to, or is the third line equal to the entirety?
Third line is equal to the entirety of the second line. So I'll go ahead and take off this curly brace here for a second. If I were to group all these things up like this.
Was that just showing that the add-all cancels?
Yeah. Okay. So basically, I'm not sure if you've heard from before, you will in Calc 2 for sure, but this is what's called a telescoping sum. What that means is basically that all of the inner terms cancel each other out. Okay. So because of that, that's why I'm able to write those two terms as many as I want. Basically making the interval or making the partition as fine or as detailed as I want. Sebastian? So yeah, that's what I want to get to at the end here. But first, I want to make sure that these calculations are okay with people. And I'm going to take silence as yes, they are. What does f of b minus f of a mean? Well, I mean, I'm not really talking about an area, really. Let's just, if I were to write down, let me give an example here. What if f of x is equal to 2x? That's just x squared. And a equals 1 and b equals 7. Then what would f of b minus f of a be? $48, right? Which, how'd you find that? So the big deal with this theorem is that this thing right here is the difference in value. So the first question I asked for, how would this work in that? What do we always use that prime to signify? That's a derivative, right? And that all comes back to this, where we invoked this mean value theorem here. I know that no matter how big these intervals are, or really how small they are, I can always pluck out a point where the derivative at that point is equal to the average rate of change over the entire subinterval. So because of that, I've boiled this function down to something involving its derivatives. So, think about what we did at the end of chapter 4, which is all about antiderivatives, and what we've done in the beginning of chapter 5, which is all about integrals. And it may not have been clear at the time, but those two things are very closely related. So differentiation and this new thing called integration are related in this very, very important way. I think it'd be more helpful if we looked at an example But if there are any more questions about this, let's take them. All right, so let's try to, actually, let me give you some more detail about the theorem. So here's what we just did basically. If f is continuous on an interval a and b, from a to b, then what you have is this, that definite integral. So basically, the thing we built up from the idea of a Riemann sum, this definite integral over that function over that interval a to b is equal to basically this capital F of b minus capital F of a. How do you think that capital F is related to the lowercase f here? Capital F is an antiderivative. So, and it doesn't matter which antiderivative it is. So one thing we talked about is that if I ask you to find the antiderivative of a function, and this theorem says it basically does not matter which one you choose. So what's the most common way we've been talking about integrals so far? What have we been trying to find using integrals? Finding areas, right? So now, where it wouldn't have seemed like, the idea of area and the idea of slope of a tangent line are related, they really and truly are. Differentiation and integration, very closely related. Any questions here? Anyone this is not news to? All right, so let's do some stuff with this. So I want to find the value of this thing. We've already found this value, right? Anybody remember what we found before? Yeah, it's 1/3. Anyone remember how long that took us? Yeah, not nice, right? So now what we can do is this. I know that f of x is equal to x squared. Can I find an antiderivative of this function? What is it? Not 1/2 x cubed. 1/3 x cubed. And that theorem we just looked at says we can pick any antiderivative, right? For now, let's just choose the most general one because something I need you to see. So that's our antiderivative, right? So basically what this theorem tells us is that if I want to integrate this function over an interval, that's the same as me looking at this. The antiderivative of the function at the upper limit of integration minus the antiderivative at the lower limit. So we get this. And I'm going to introduce you to a piece of notation right here. What this basically says that, all right, I have taken an antiderivative, and those are my limits my limits of integration that I'm going to substitute it for. Oh, I left off the state, didn't I? So if I plug in 1 to this expression here, I get 1/3 plus c. If I plug in 0, I get 0 plus c. So when all is said and done, I get 1/3. Sebastian. Anybody want to take that? What happened to the x cubes? That could have been more clear about, I suppose. Right. So, and that's, I really shouldn't be blowing past this notation like this since I just introduced it, but the 1 and 0 on the outside of that bracket there means I want to make that substitution. So what really happens is this. I get 1/3 times 1 cubed plus c minus 1/3 times 0 cubed. minus, or no, plus c. So this right here is my f of b. And this right here is my f of a. Capital F of b, capital F of a. Sure.
Are you adding the, let's see,
Oh, this is the.
we did integration.
That's one thing I wanted to bring up. So what happened to the plus c in this case? It canceled out, right? So what does that mean about whether we should include it from now on? It will always fall away, right? So this is a shortcut that a lot of mathematicians take, and the one that I advise us to take is we can choose any antiderivative we want, right? We might as well choose the one where c equals 0 because we know it's just going to fall off after we evaluate it. Could I call C 31 here? What would happen to it? Right, so it's always going to go away. So understanding that, most mathematicians, or I would like to say all, but I can't promise that. Most mathematicians just, they know it's not going to be part of the end product, so we just let it go early. Make sense? All right. So this right here was a thing that we could not have dealt with in terms of just Riemann sums, right? But now we can. Now knowing that definite integrals are related closely to this idea of an antiderivative, that lets us handle. So what's the function here that I am integrating? So I got f of x equals e to the x. So if I want to find this integral, what do I need to continue? What is the antiderivative of e to the x? E to the x. I'll do the x plus c for now, but really I know that I don't need to, as I make this calculation, I don't really need that because I know it's going to fall away. So the antiderivative is e to the x. I'm going to evaluate that from 1 to 3. So how is what's my final result going to be? E to the third minus e to the 1, or yeah, e cubed minus e. How? I mean, there are ways to rewrite it. I think that being, I'm okay with that one. If you like to factor out the greatest common factor, you can. Any more questions here? All right. All right. So I'm going to want to find the area under the cosine curve. Interval from 0 to 2. So the way this is phrased, can I relate this to an integral somehow? Let's set up the integral first, and then we can evaluate it. So we should probably, what are the things we need to know to set this integral up? Yeah, so what's the interval? Not really 0 to 2. Because really I don't want to find that full area. I want it to vary. I want to have some control over where that interval is. So I don't want b to go any higher than 2, but maybe I want to find the integral from 0 to 1 or 0 to pi over 2, something like that. So a little bit different, but we got our interval. X is going to vary from 0 to some b. What other information do I need to know about this to set up an integral. Need another function. What is it? X equals cosine of x. Anything else we need to look at? Or can we set up this integral now? So we have the interval, so I can use that. I'm going to integrate from 0 to b. We know the function we're going to integrate, cosine of x. We know, we're going to integrate with respect to x. So I think our setup for our integral only depends on those two things. We want to know the limits of integration. So what's the interval we're integrating on? And you need to know the function that you are integrating. So now can we evaluate this thing? What do we need to do with cosine x to continue? I need the antiderivative. So from here, what is the antiderivative of cosine x? Sine of x plus c. Okay, so knowing I can let go of the constant or just make the constant equal to 0. Now what I'm doing is this. I'm evaluating this function sine of x from 0 to b. So from here I get sine of b minus sine of 0. What is the sine of 0? So just get the sine of b. So if I want to find the area under the cosine curve, from 0 to b, I can just take the sine of b and get the same result. Any questions here? Moving on. So let's give you a few properties here. So this basically comes from, everything we've done for the last several days has been definite integration. Now we're talking about something that we haven't really talked about before, which is indefinite integrals. So the main difference between those two things is, actually, I'll ask you. The integral I'm showing you now, what's the difference between this integral and all the other ones we've done up until now? Yeah, there's no bounds, right? There's no interval. So, and this is a piece of notation that was actually really hard for me to avoid using when I was talking about antiderivatives because it's so common. But when you're talking about antiderivative, this is a pretty common way to represent it as this thing called an indefinite integral. Because now we know that the antiderivative of a function is very closely related to its antiderivative. So hopefully I'm not showing you anything monumentally new here. Are we okay with what this first bit of notation is telling us? Just to be clear, how are the functions capital F and lowercase f related here? Capital F is the antiderivative of f. Or if you want to say it the other way, f is the derivative. Lowercase f is the derivative of capital F. And basically this line here just says that those two things are equivalent. So, and sometimes because of this, you will hear the antiderivative function being referred to as its indefinite integral. Those terms get used interchangeably pretty much everywhere. All right. So I'm going to talk about here though. If I take the definite integral of a function, provided that a and b are both just known, like they're numbers, what do I get when I integrate a function over some fixed interval? You get some kind of, what do you mean by that? You get a sum. Okay. I think, okay, let's try to think about how to ask this without giving it away. What's the difference between these two things here? If I take the indefinite integral function or the definite integral function, what's the difference between? Right. So the big distinction I wanted to take away is this. I get a function in this case. I get a value in this case. So one just gives you a number, essentially. The other one gives you a new function. Any questions on that distinction? Why they do different things? Okay. So let's find an indefinite integral here. So how can we handle this thing? Can we do it one term at a time? Okay. Let's break it up that way first. So 10x to the fourth dx minus the integral of 2 secant squared x dx. Can we find the integral of 10x to the fourth dx? We got 2x to the fifth. You okay with that? Let's see. How about the right term? Minus 2 tangent of x plus some other constant, I'll call it d. Is it weird that I have two constants in here? Really, we can just collect them together. If c is an unknown constant and d is an unknown constant, I'm just going to add them together. Might as well say I just have some unknown constant. So really, I mean, I asked for the indefinite integral, but really what you gave me was this thing we know is an antiderivative. Now we know they're one and the same. Any questions? Okay. This one, have we done this before? I know we did, and I cannot remember off the top of my head what the answer was, but I know that it took us more. I think didn't this like span 2 days, and I ran out of room doing it. But now, based on what we know, can we find this integral in a different way? All right, let's do it. How do we handle this thing? All right. So if we know our function is x cubed minus 6x, what is the antiderivative? Fourth x to the fourth. Minus 3x squared plus c. So then I can do this. Integral from 0 to 3 of x cubed minus 6x dx is equal to this function, 1/4 x to the fourth minus 3x squared, evaluated from 0 to 3. 3 to the fourth is 81 minus 3 times 9 minus 0 minus 0. So 81/4 minus 27. That's Sebastian. Yeah, absolutely. Yeah, absolutely. So, I mean, not only is it more efficient, but it's more powerful. I mean, think about the second example we did today was, I think, this. The integral from 1 to 3 of e to the x dx. There's no way a Riemann sum gets you there. So, yeah, this thing is, works in a lot more cases. And in the cases where they both work, you would never, ever do that limiting Riemann sum thing. I mean, I struggled to get this calculation on a single slide last time. Any questions on this? And I think even going back, looking at some of the things that are on the homework, actually, these two are bad examples. Bottom line is just right tool for the right job. I don't think that, like, so this one, I think one of the integrals was integrating some square root of 4 minus x squared. I don't think you have the weapons to take an antiderivative of this thing yet. So it depends on the circumstances what you can use. Any questions here? Right. So let's evaluate this thing and talk about what this means in terms of area. So I want to integrate from, actually, I need to rewrite that. What's the function where, actually, you tell me, where, how should we start approaching this? Let's do it. So our function is this thing here. What's the antiderivative of 2x cubed? One half x to the fourth. How about 6x from our negative 6x? Negative 3x squared. And this last one might be a little mysterious. Close. 3 times the arctangent of x. Plus c. I think this, again, the trickiest thing that's going to be with indefinite integration is just in general, it's a much simpler thing to look at a function and go towards its derivative. It's a much more complicated thing to go the opposite way. Every continuous or every differentiable function has a derivative, obviously, but they don't all have integrals. At least not a closed form indefinite integral you can find. The example you'll probably see sometime soon is this. If f of x equals e to the x squared, if I asked you, you could probably find that derivative relatively quickly. But this thing right here does not exist. All right, so we got this antiderivative. Now what do we do with it? What do you mean by that? I don't think I gave a name for its format, but okay, here's the antiderivative. which I know I need. Well, what specifically am I going to do with it? Right, so I'm going to evaluate it at both endpoints. So I'm going to get 1/2 of 16 minus 3 times 4 plus 3 times the arctangent of 2 minus 0 minus 0. What's the arctangent of 0? Zero. So I should just get 8 minus 12, so minus 4 plus 3 times the arctangent of 2, which I'll just leave exact unless I'm with it. All right, so this is the value of the integral. I would like to know if this thing is positive or negative. What is the arctangent of 2? 1.107. So this is going to be about negative 0.6-ish. All right, so we got an approximate value of this integral is like negative 0.67. Now, in terms of areas, what does that mean? First of all, for an area, so for an integral to give you a negative value, what does that mean about where the area is? Sebastian? All right, so does that mean that all of the area is below the x-axis and it has, and we can measure it to be 0.67 square units? Right. So, I mean, without looking at this function, we can almost, I mean, if you just plug in, if we were to graph this, we would certainly find that there is area above the x-axis. But again, where is there more of it? Where's the greater area, above or below the x-axis? Below. In terms of getting a better idea as to where that area lives, we'd have to look at a graph, but if we're just evaluating this integral all at once, remember that, negative areas, I mean, there's such a thing as signed area, which I'll remind you of again. Signed area. Which says that area might be negative, depends on where it lives. How are we doing so far? Let's do one more and call it a week. All right, so let's handle this thing. How do we do this? What kind of function has a derivative that looks like that? Is that even the question I should be asking you? There is no quotient rule of integration. Not that I have. Oh, it might be. So we might be able to reverse engineer it that way. So I think that's that's always a good thing to look at. I mean, I have no idea how I would integrate that directly, but what we can do is this. I can look at this in terms of 3 separate functions, all integrated over the interval from 1 to 9. And from there, I can even simplify them further. The integral of 2 dt plus the integral of radical t dt minus the, actually that one's not going to simplify. All right, this leftmost term, what is the integral from 1 to 9 of 2? How'd you get 16? Right. This is one of the properties we talked about last time, which was, or last week, that thinking about this in terms of an area, for example, that's a rectangle with a constant height of 2 and a length of however long the interval is. For the next two, we're going to have to think about in terms of antiderivatives. So what is the antiderivative of the square root of t? That's a property of integration. So if you think about what, if I were to graph this, constant function 2, integrating from 1 to 9, this area is what shape? Right. How do you find the area of a rectangle? Right. The height is 2. The base is whatever the difference between those two x values is. So that one's going to end up being 16. All right. What is the antiderivative of t squared, or not t squared, square root of t? How did you do that? Right. And I think everything follows from there. So one more thing I'm going to emphasize is it's really, really important to rewrite things. Especially the power rule is hard to use if you don't have it written in terms of an exponent. So in this case, this is going to be equal to t to the 1/2 plus 1 over 1/2 plus 1. So that's t to the 3/2 over the reciprocal of 3/2. So you get 2/3 t to the 3/2. So plus 2/3 t to the 3/2, evaluated from 1 to 9. And the last one, what's the integral of that last term? -1 over t. Again, let's look at power rule with a rewrite. It'll be t to the -1 over -1, which cancels out the negative sign on the outside, and I get plus 1 over t, evaluated from 1 to 9. We okay with this? So just for the sake of completion, let's go ahead and hammer out this result. 16 plus 2/3 times 27 minus 2/3 times 1 plus 1/9 minus 1. If anybody wants to approximate that, you're more than welcome, but I'm not going to keep. Any questions before we break? All right, everybody have a good weekend. Safe holiday, and I'll see you on Monday.